Okay, we're in Calc BC, coming back to lesson 3.7, finishing with example 4. You can see this is really a very similar problem to number 3, example number 3, except this graph is no longer position versus time, it's actually velocity versus time. And as we work this out, we can see this picture. We don't have an equation, nor do we need an equation. The picture is definitely enough. When do we have the figure move to the right? When would a particle move to the right? Well, it moves to the right, I hope you remember, when v is greater than 0. It moves to the left when v is less than 0, when v is negative. And likewise, if v is 0, then of course you come to a stop. But of course, as we look here at number 4, I hope you can see that velocity is y values. For example, at 2 seconds, maybe this is in seconds, at 2 seconds you can see that our velocity would be 6 feet. So, unlike what we did before, for the example 3, velocity was tangent line slope in a position graph, but not here. If you wanted to know what the velocity, say at 2 was, you'd just look at the y coordinate, the y value there. So the big question is, when is velocity greater than 0? When is velocity greater than 0? I hope you would agree that it's whenever your y values are greater than 0. That is, when this velocity curve is above the time axis or x-axis. Likewise, velocity is negative when the curve is below the x-axis. So we're going to answer these questions right now, but there is one other issue that we really need to clarify. We really need to deal with this issue. What is this point right here? It's an x-intercept. I'm going to put a red dot right there. So very often kids will look at that and they'll say, well, it's 1/2. We have to be very careful. We're not guaranteed that that really is a half. It very well might be just a little bit off, and we're going to see actually it is. This segment, if we were to look right over here at this segment, you can see it's a line segment, and that means we could describe that as y equals mx plus b. Well, what is our y-intercept, our b? Well, that would have to be -3. How about our slope? Well, you can see going from -3 all the way up to 6 is actually going up 9 steps. You can see each of these tick marks are going by 3, so it's 3, 6, 9, or you could do 6 minus -3. So we're going up 9, but then how much are we moving to the right? Well, you can see we're moving to the right 2. So it doesn't take too long to see that we have 9/2 for our slope. And we have this so that we can say, when is velocity going to equal 0? We can set that in there, and then we can solve. And we can add a 3 to both sides. Get 3 is equal to 9/2 x. Maybe multiply by 2/9. And it only takes a moment to see the 3 cancel the 9 there. You'll get 2/3. So this x-intercept is really 2/3. And you could see we would have been in a world of trouble if we just would have assumed that we were passing through the middle. Just like in geometry, you can't assume that you have a midpoint just because something looks like a midpoint. This is very similar thinking here. But now I know when my velocity curve here is above the x-axis. That's where velocity is positive. It's going to be from 2/3 to 6. Where else? Well, from 8 up to 10. And tell you what, with the 10, I'm actually going to put closed brackets in there. That indicates that 10 itself has positive velocity. Take a look here. You know, if you were to say, what is v of 10? V of 10 would be positive 6. So that's positive velocity. That means that you'd be traveling to the right. By way of comparison, look at v of 8. If you had v of 8, you'd say, well, that's 0. That's not positive. So I really cannot say that we're traveling to the right there. It actually means that you're stopped. Likewise, we can say, when are you going to be traveling to the left? Well, that's when you're below the x-axis. So we can say 0 to 2/3. Again, very similarly, I'm going to put a bracket around the 0, because v of 0 equals -3. A negative velocity means that we are traveling to the left. So at 0, you truly are traveling to the left. Anywhere else, well, you can see between 6 and 8, you can see our curve is below the x-axis. So that's all well and good. Hope that is making some sense right now. But there's more to the story. We're going to leave off with B. We're not going to do that just now. We want to talk about acceleration. Now, acceleration, and you want to know when acceleration is positive, when it's negative, and when it's 0. The acceleration, as you look at this, you can say, well, how do I know what's going on? Acceleration is the derivative of velocity. And that, by the way, is tangent slope. So you're saying, where do we have positive tangent line slope? Well, I hope you can see you're going to have positive tangent line slopes in a number of locations. Here and here. So what I'm going to do is I'm going to say we're going to be between 0 and 2. And also 7 and 9. Now I'm not going to use brackets here because at a corner your derivative won't exist. And likewise at a left endpoint, I mean, we could make an argument and talk about one-sided derivatives and talk about that existing. But let's just keep it entirely open here. This is where you'd have positive tangent line slopes. You'd say, well, where would we have a negative tangent line slope? Well, I hope you can see anywhere between 4 and 7. And by the way, we could actually find those slopes very, very soon, and we will. 0, I hope you can see, is where you have a horizontal line that's between 2 and 4. Likewise, you'd have that between 9 and 10. And right there, you'll know where your acceleration is positive, negative, or 0. Now, to start off, we already saw that this slope, you might remember, we found it to be 9/2 right here. Let's go ahead and take a look at this green segment that I'm going to highlight over here, this negative portion. Let's count the rise over run and see if we can figure that out. Looks like I'm going to go down 9 and right 1, 2, 3. So if you go down 9 and right 3, that's going to be a slope of -3. Tell you what if we were to, let me erase this little part here and just come back and find the slope on that last positive section, maybe make that blue. Well, you can see what's your rise over run. Well, your rise over run, you're going to go up 6 steps. You can see you're going from -3 to +3, and you're going to go right 2. So you're going up 6, right 2. That would be a slope of +3. And that's actually what your acceleration will equal for those specific values. I bring that up because in D, we're going to graph this right now. For D, we're going to actually make a graph of our acceleration. Okay, so Tell you what, I'll move this over just a smidge too. And we'll say here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we'll say 1, 2, 3, 4, 5. The biggest slope I saw was 9/2, which is 4.5. The smallest slope that I saw, the smallest acceleration, would be -3. So here's our acceleration in time. I'm going to change to red just so that it really stands out. You can see that between 0 and 2, our slope was 4.5. So I'm going to have open circles here. And then what? Well, between 2 and 4, my slope was 0. Between 4 and 7, our slope was down here at -3. Oops, my pen's having a little bit of an issue. There we go. And between 7 and 9, we're going to be at +3. Then between 9 and 10, we're going to be back at 0. So that's part D. That's what the graph of the acceleration function would look like. Please do take a moment to copy these two very, very important guidelines here. A particle is speeding up. A particle is speeding up if velocity and acceleration both have the same sign. Either both are positive or both are negative. So a particle is speeding up. We could also say speed is increasing if both acceleration and velocity are both positive or both negative. By way of comparison, if a particle is slowing down or speed is decreasing, that happens if velocity and acceleration have opposite signs. Here's a little scenario that can be confusing for a student. Let's just say for a moment that your velocity was 3 feet per second. And let's just say that your acceleration was 1 foot per second squared. If that were the case, you'd be moving to the right, and 1 split second later, your velocity would increase 1 foot per second. You'd then be going 4 feet per second. And you'd still be with a positive velocity going to the right. You'd speed up. That's if velocity and acceleration are both positive. But what if acceleration was negative? You're traveling to the right 3 feet per second, but 1 second later, your velocity drops 1. It's no longer 3 feet per second, it's 2 feet per second. You're still traveling to the right, but you've actually slowed down. You're now only going 2 feet per second. So let's just say, for the sake of argument, that velocity was negative. Let's just say you're going -3 feet per second. Well, -3 feet per second means you're going to the left. And 3 feet per second, you're going over like 3 square tiles in a school to the left in 1 second. 1 moment later, 1 second later, you drop another -1. So -3 minus 1, it's -4. Now your new velocity would be -4 feet per second. You'd still be traveling to the left, but you sped up. You're now going over 4 floor tiles in a second. That's if they're both negative. Finally, what if you have opposite signs? -3 feet per second, you're traveling to the left, covering 3 square tiles per second, but you add 1 foot per second there. 1 moment later, you're now at -2 feet per second, still traveling to the left, but now you're only doing 2 feet per second. So I wanted to explain that. I think sometimes kids will almost say, I don't quite get how, two negatives, a velocity being negative and acceleration being negative, could actually lead us to speeding up. I'm going to make a continuation of this video to do part B in just a moment. Hopefully when we see that, we'll be able to get some nice closure.